My name is Jess Silver. I'm a scientist with the Natural Capital Project, and today I will be introducing you to the Coastal Protection Toolbox, specifically focusing on the nearshore waves and erosion model. This tutorial will introduce you to the InVEST Coastal Protection Toolbox with specific focus on the nearshore waves and erosion model. Coastal and marine habitats, like the marsh pictured here, can function as natural breakwaters, attenuating waves and storm surge. Understanding the role that these nearshore habitats play in protecting coastal communities is becoming increasingly important in the face of a changing climate and growing development pressure. The InVEST Coastal Protection Toolbox and the Nearshore Waves and Erosion model quantify the protective benefits that natural habitats provide against erosion and inundation in nearshore environments. When storms occur, waves and storm surge can cause water levels to rise, which can result in subsequent erosion of coastline. The presence of natural habitats during these events can function to attenuate waves, reduce water levels, and help prevent erosion. The model takes into account information about characteristics of the site, the storm conditions, and the ability of different marine and coastal habitat types in the area to reduce waves and storm surge. The Nearshore Waves and Erosion model is part of the InVEST Coastal Protection Toolbox, which is comprised of two models, the Coastal Vulnerability Tool and the Nearshore Waves and Erosion model, which this tutorial is focused on. The Coastal Vulnerability Tool is often used first to understand large-scale patterns of vulnerability to coastal hazards in a region, to learn about the general environment and evaluate scenarios. Then, regions of particular interest are examined in greater depth using the Nearshore Waves and Erosion model. The model requires inputs about site characteristics. These include tidal elevation, the type of shoreline, is it muddy shoreline or a sandy beach, and the presence or absence of a dune system. The model also takes into account information about biotic features, which includes the location, the areal extent, and the density of biotic habitats in the region. Storm characteristics such as duration and storm surge elevation, as well as more specific details, including wave height and wave period information if the user has this. And then also information about social data, so numbers of people and property values along the coastline, and potential management actions, including the restoration and removal of habitat. The primary model outputs are avoided, eroded, and inundated area, avoided number of people affected, and avoided property damages. So here I want to show you an example from the BELIZE case study where this model was applied. In BELIZE, the model was run for the entire coastline as well as the atolls and islands. And the model was evaluating changes in coastal protection services associated with different management scenarios. These scenarios differed from one another with respect to the extent, density, and location of natural habitats, including mangrove, coral, and seagrass beds. The coastal protection model evaluated how changes in these habitats were reflected in changes in the delivery of coastal protection services along the coastline. In this case, valuation was in terms of avoided damages. The primary limitation of this model is that it's a one-dimensional model. So the model is run for specific transects, shown as the red line in the panel on the left, and the model outputs results along those transects. In the top panel, you can see a depth profile as you come into shore, and you can see the location of your natural habitat, in this case, marsh, in the green. The bottom panel shows a profile of wave height as you are approaching the shore. and compares a scenario in which you have marsh present in the green and marsh absent in the blue. And you can see in this case that the marsh functions to significantly reduce the wave height as you come into shore.